know what latitude and longitude are for, positioning ourselves anywhere on the globe. But did you also know that the latitude lines give us measurement for distance and therefore speed? So how do they work? If the Earth were flat, this would be easy, right?
Of course, if Earth really were flat, then we could just put a grid over the map and label the two axes, perhaps letters for the y-axis and numbers for the x-axis. Life would be pretty straightforward. As we move around the world, we just use the y-axis and x-axis as appropriate. This isn't actually dissimilar to how latitude and longitude is used in practice, but what's important to understand is how the lines are created. Contrary to flat earthers' belief, if we continue to sail west, we won't actually fall off the edge of the world. What really happens is we move from the left of the chart to the right of the chart. That's because line 1 and line 19 are essentially the same place. In the same vein, if we think about how we've unwrapped the globe to create a flat chart, all of the vertical lines are running from one spot on Earth to another. If we travel northward up any of these, we end up at the same place, the North Pole. The whole of line M is the North Pole, and line A is the South Pole. So let's take a look at how these lines are created. The theory behind latitude and longitude can be traced back to this guy in the 3rd century BC. By the 2nd century BC, this chap, Hipparchus, started using the maths to uniquely specify places on Earth. So let's look at the horizontal lines that run across the chart, the ones we use to establish how far north or south we are. To find out how they are created, we have to go to the centre of Earth. Once there, we can easily see that we have to rotate 180 degrees to change from pointing south to pointing north. If we protrude lines out from the centre of Earth to the surface at 90 degrees, we can create a line around the globe at its fattest point. Of course, we all know this line. It's the equator. It has effectively split the globe in two, the northern hemisphere and the southern hemisphere. This is important in terms of understanding how latitude works. The equator becomes our start point. In latitude terms, it is 0 degrees. The easiest way to see what happens next is to go back to the centre of Earth. Now that we have a start point, we can create lines that run parallel with the equator, hence their name, parallels of latitude. Each one can be referenced using its angle back to the centre of Earth. This can be done to a maximum of 90 degrees north, straight up, or 90 degrees south, straight down. Now let's unroll Earth and see what that looks like on a flat chart. In this view, we can now see how we can reference ourselves anywhere, in degrees, north or south of the equator. In addition to the equator, there are a few other named parallels of latitude that we've probably heard of. Now we know how the lines of latitude are created, let's look at the lines of longitude, the ones running vertically across the chart. Back to the centre of Earth. If we were to walk around the equator, we would complete a circle, 360 degrees. If, at every degree, we ran a line around the globe, passing through the North and South Pole, we would effectively create our lines of longitude. Pick any one of those lines and we could divide the world in two, this time creating a left and right half, or west and east hemisphere. And that right there is the challenge. Unlike the lines of latitude, where there is a natural place to divide the globe, with longitude, we could pick any one of the 360 lines to be our start point. In fact, for a long time, different nations used different lines as their start point, each producing charts that worked from their definition of where east and west met. That's where these guys come in. In 1884, at the catchily titled International Meridian Conference in Washington, they came together and voted on a standard for the world to adopt. The chosen meridian? Greenwich, our zero marker, where east meets west, the prime meridian. Back to our flat map, let's mark the prime meridian. Now we have our start point, we can count up as we move each degree in either direction. As we move west, we add westerly longitude lines. We continue to move west and add lines of longitude. We eventually get to 180, half a complete rotation. If we carry on moving in the same direction, we move from the west to the eastern hemisphere. The degrees start reducing as we continue to move round until eventually we get back to our original start point, 000 degrees. So now we can ditch our battleship's layout and replace it with our newly learnt north-south, east-west axis. We now have a start point for our positions, the cross in the middle, which is neither north or south, west or east, 0 degrees. Everything builds out from here. Breaks the globe into 4 primary quarters: northeast, southeast, southwest, northwest. With the addition of latitude and longitude, we can start to narrow down our position on the globe, but the scale is still not suitable for the precision required. Let's put a chart over our grid and dive in. Now we are looking at a chart of a specific area. Let's take a closer look at each of those scales. First, let's take a look at the latitude scale. So here's the 50-degree north latitude. We know it's north because we're looking at a chart in the northern hemisphere. As we move north up the chart, we get to the next degree of latitude, 51 degrees in this case. Of course, each degree covers quite a large area, so we need a way to divide them up further. To give you a sense of size, the 50-degree latitude is in France, while the 51-degree latitude is in England. Crossing the English Channel at its narrowest point between Dover and Calais covers about 1/3 of a degree of latitude. So we need a way to break each degree down. Each is divided into minutes, 60 of them, annotated using a single quote. As we move north, the minutes increase until we hit the next whole degree. Why 60 minutes, you're thinking? Remember, this system was created when all numbers were worked in units of 12 or 60, which was devised with some logic in mind. 12 or 60 can be divided by 2, 3 or 4, halves, thirds and quarters, without the need to use any fractions. The same measurement principles apply for longitude, our west or east scale. Here we are on the prime meridian, 0 degrees. So if we go right, we are increasing our east longitude, left, our west longitude. So let's take an even closer look and dive right into this chart. We can see that even measurements of minutes only give us a certain amount of accuracy. Each orange bar on the chart represents 1 minute of longitude. Most charts nowadays break the minutes up using a decimal scale. That is, each one is broken into units measurable and dividable by 10. On this chart you can see that there are 10 individual units between each minute. Most GPS systems can and will report latitude and longitude using decimals to break down the minutes. Many charts, like this one, are of a scale that won't cover a whole degree. In fact, there may not be any whole degree lines of latitude or longitude on them. The only units of measure will be in minutes and their decimal. If this is the case, the appropriate degree for the chart will be written on the scale. What's important to remember is that this is not where the degree line is, rather just a note so you know what degree area you are working in. So let's use latitude and longitude to precisely locate a position on the chart. It's a simple process of narrowing down our position in 4 stages. Take this dot. Firstly, we know roughly in the world where we are, i.e. what hemisphere. In this example, we're in the northern hemisphere, our latitude, and the western hemisphere, our longitude. Stage 2 is to find the correct references for degrees. Here we are 50 degrees latitude and 001 degrees longitude. Happy we've established that, we move on to stage 3, narrowing down the minutes. When looking at the latitude scale, because we are in the northern hemisphere, the scale is moving upwards. Therefore, we need to be looking for a number to the south of our position. in this case 43 minutes. Likewise, when looking at the longitude scale, we need to consider which hemisphere we are in and therefore which way the scale is going. In this example, we are in the Western Hemisphere, so the scale is going from right to left, i.e. west. So we need to use the number to the right of us to ensure that we are focused on the correct minute, in this case 37 minutes. So we've narrowed our position to a single square on the chart. Lastly, stage 4, we can get really accurate by using the decimal scale between the 2 minutes, remembering to read them from the smaller minute to the larger minute. So our latitude decimal is decimal 30 and our longitude decimal is decimal 50. So there we have it. The latitude and longitude of our position in full is 50 degrees 43 minutes decimal 30 north, 001 degrees 37 minutes decimal 50 west.